Poisson regression models are often used to model counts in a contingency table. This is done by treating the cells of that contingency table as essentially the results of independent Poisson random variables. Then we use the row and columns of the corresponding contingency table, the corresponding variables, as essentially explanatory variables in our model to model those corresponding counts. Let's take a look at an example to help explain that further. So we're going to go back to using the Larry Bird data set once again. Now with the Larry Bird data set, of course, we have the second free throw attempt, its outcome, made or miss. First free throw attempt, its outcome, made or miss. Now let me jump over here to 10. And so I can enter the contingency table in like we would normally do. But now I need to change the data format to a format that the GLM function can use to estimate a Poisson regression model. And to do this, a little bit strange, I say as.table, c.table, and basically what this does, it changes or has R recognize that this is indeed a table of counts. And then when I apply as.data.frame with the corresponding result, my data format is actually changed to this, where now I have all the possible combinations of the first and the second variables, and I have a new column, let's call it freq for frequency, which contains the counts that were in my contingency table. We are essentially then going to use this freq column then as our response, and first and second as explanatory variables in our model. So to do that, let's use the GLM function, formula equal freq tilde first plus second. So notice here I'm not including an interaction term, at least right now, between these two variables. My data is in Bird, family equal Poisson, link equal log. I put the results into mod.fit, and then I summarize mod.fit 1 specifically. And let me come back over here to my Word document. Here's the actual formal statement of the model. Perhaps I should have done this first. Sorry about that. Log of mu, where mu is my count for the contingency table, is equal to beta 0 plus beta 1 times an indicator variable for the first variable, plus beta 2 times the indicator variable for the second variable. This is essentially a model under independence because I do not have an interaction between the first and the second variables. First free throw, second free throw variables, to be more specific. Okay, so here, for example, is now beta hat 2, and then I can use the results to write out my estimated Poisson regression model as what we've seen before. What about getting the estimated mean counts then for each of the cells? Well, we can go back to using the predict function for that purpose. Object equal mod.fit1, where the results from GLM are stored. New data equal, I'm just going to put in my original data frame itself because I want to predict for what happens for the first free throw attempt and the second free throw attempt. Type equal response, and so here are my mu hats. And how this is represented is in the exact same order as what we saw with our data frame right here. So the first value given is for made second, made first free throw, and the estimated count is 252.11 under independence. Now, again, this is a model under independence. Let's go back to using some stuff from chapter 3 and see if we get similar results. So in chapter 3, we learned about a Pearson chi-square test for independence. And to do this test, of course, we need to calculate the estimated expected counts under independence. One way to have R do this automatically is to use the chi-sq.test function, where again I say x is equal to c.table, so my original contingency table. I do not want the correction that comes with it by default. put the results into Pearson.test, and if I extract out the expected component of the resulting list, this is what I get. Notice I have 252.11 for the second free throw made, first free throw made, and it matches exactly what our Poisson regression model gave us. And in fact, all these counts in this contingency table match with what we had. Do that. Unfortunately, now my pen's not working right. There we go. And so essentially we're getting an equivalent analysis. We have a Poisson regression model under independence. We do the Pearson chi-square test to test for independence, and we get the same results. How about we estimate the model under dependence though? We use exactly the same code, but I'm going to put the results into mod.fit2 and also include the interaction between first and second. Here's my corresponding output. So notice I have now the interaction term that's estimated from my model. Now notice here my residual deviance. It's about 0. I have 0 degrees of freedom with it as well. And so what we've just done here is actually estimate a saturated model to our data. Why? Well, our data frame has 4 rows to it. Essentially, we have 4 Poisson observations corresponding to the first and second free throw made or misses. So, because of that, 4 observations, I'm estimating 4 parameters. That's why I have a saturated model here. Then, well, what would be the estimated mean counts? Excuse me. So I can use the predict function with the results from mod.fit2, new data equal bird, look at my predicted counts, or estimated mean counts, I should say. They're exactly the same as what was observed. We have a saturated model. How about we perform a hypothesis test for independence now in this Poisson regression model setting? So what we need to do is, and I guess I didn't write out the full model in terms of the model that has the interaction term in it, but if we can think of it this way, this is my estimate of beta hat 3. So to do a test for independence, I would need to test, is the beta 3 value equal to 0 or not? So here are my hypotheses. I could use the capital ANOVA function for my test, much the same way we've done elsewhere. Here's my -2 log lambda statistic, the corresponding p-value. So there's not sufficient evidence to indicate that there is dependence in our contingency table. I could use the little ANOVA function as well, where I put the HO model and then I put the HA model there. Of course, I get exactly the same results. And we can compare it to what we did in Chapter 3 when we used the VCD package. We had a likelihood ratio test statistic here. And guess what? Exactly the same. So what this shows you is that we have this nice equivalence between a Poisson regression model and to what we were doing previously with the likelihood ratio tests in Chapter 3. And of course, remember, we also got exactly the same results here with respect to using a multinomial regression model too. So we see some interesting equivalences. I'll talk more about those equivalences shortly. Now, some terminology here. Often when you are using a Poisson regression model to model contingency table counts, meaning we essentially have, you could say, explanatory variables that are only categorical in nature. People will often not refer to this as a Poisson regression model, even though it is, and instead they will refer to it as what's called a log linear model. Why? Well, think of it again how we formulate our model. Log of mu. Okay, so there's the log part. And then we have a linear combination of the betas with the x's. There's where the linear is. It's just a terminology that people often associate with these kinds of models. It's somewhat unnecessary, but that's often the way it's spoken. Now, also with these kinds of models, when we're working with a contingency table, one often states our model in a different formulation. This formulation is very, very similar to what is often referred to as a treatment effects type of model that's used for ANOVA. So here's how you will often see these models stated. Log of mu sub ij, where I corresponds to the row number, j corresponds to the column number. That's set equal to lambda. Lambda is an actual, you could say, regression parameter, like our beta 0, plus lambda sub I with a superscript x. The x there doesn't mean that I am multiplying it to, or I'm taking it to the x power. Rather, it's just a way to designate this is a lambda associated with the row variable. I put an I subscript there to denote the row number. And then I do a similar thing over here for the column variable as well. This would be the model under independence. So for example, notice how I have I equal 1 and 2, j equal 1 and 2. So I could actually write this as log of mu 2 is equal to lambda plus lambda 2 to the x plus lambda 2 superscript y. The model under dependence then is exactly the same, but now I have an interaction term there. Notice how I have two subscripts, I and j, and then I have the superscript is x and y to say, hey, this is an interaction between x and y. Each of these lambdas are parameters that we would like to estimate. But in the end, we're going to actually have more parameters than we have, let's say, observations in our data frame. And so because of that, various restrictions need to be put upon these lambdas. The most common is let's let lambda 1 super x be 0. Similarly for y. And then for the interaction term, I need to set 3 of them to be equal to 0. And if you've heard of in another class identifiability restrictions, this is what we need to do that, since we have more, we've written a model out with more parameters than there are essentially rows to our data frame. And in the end, the key thing to actually understand, and let me actually come down here. The models are equivalent. There's just two different ways to write out the model. So, with respect to our original Poisson regression model, we wrote out our model like this, where first miss was an indicator variable corresponding to the first free throw, second miss is an indicator variable corresponding to the second free throw attempt. Now we know that first miss is equal to 1 when the first free throw is missed, 0 otherwise. Come back up here. Lambda 1 superscript x is equal to 0 for level 1 of my row, which would be first made. And then lambda 2 superscript x is what we're actually then going to estimate. What's that estimate? Negative 1.68. You could do a similar thing for the column variable as well. And so this is what I did here in terms of writing out then the model in this alternative format. It's exactly the same. All it is what's often referred to as as I've said before, a treatment effects formulation of an ANOVA model. To some respect, I don't really think it's really necessary to differentiate between the loglinear and the Poisson regression model way of expressing this. I am discussing it here simply because when you maybe look at other books, when you look at, let's say, other papers, or when you talk to other people in terms of how they actually write out the model, they might write it out differently than how we do it. And the reason is because they use the more, let's say, traditional loglinear model formulation of the model. Now, we could use our models For larger contingency tables, we looked at a 2x2 contingency table. We could do it 3x3, 4x4, but we also could do it for, let's say, a three-dimensional contingency table, or three-way table, meaning that we have three variables. So for example, here is a 2x2x2 contingency table where we have this third variable z, which corresponds to what's often referred to as a strata or layer variable. You can have a four-way table, you can have a five-way table, and these Poisson regression models can be used for that particular situation as well. You can have interaction terms between, let's say in this case, x and z. You could have a three-way interaction term between x, y, and z as well. So you can see there's a whole bunch of different kinds of models that one could look at in these kinds of situations. Now, for all these situations, both Poisson regression models and multinomial regression models can be used to model this. Again, just think of each of the rows, columns, or strata as categorical explanatory variables and set up your model accordingly. Now, when you use a Poisson regression model or a multinomial regression model, you'll get the same results. Why? Let's consider the two-dimensional table situation, meaning you have x, you have a row, you have a column variable. The joint probability distribution of I times j independent Poisson random variables, conditional on their sum, meaning the total count, like the total number of free throw pairs that Larry Bird did, that distribution ends up being a multinomial distribution. Kind of cool that that happens. The same thing happens when you have a three-dimensional table, four-dimensional table, and so on. To fully understand why this happens, it's very, very, very useful to have a mathematical statistics course in your background. For those students who take my course, I have some that do and some that do not. For those that do, take a look at the next couple pages, and I actually go through the proof about why this result of this equivalence between a Poisson and a multinomial distribution occurs. For all students who are taking my course, they're responsible just simply to understand that this result occurs and that we'll get equivalent outcomes or equivalent analysis results. So here's all the proof there. And I actually, in my program for corresponding to the Larry Bird example, I actually show you how you could estimate these models different ways and get the same results. Okay. So now we're to a point where everyone is responsible for the following content, and that is, well, is there an advantage to using the Poisson model or the multinomial model, or vice versa? The answer is largely no. There's one kind of situation where using a Poisson regression model is a little advantageous, and that is with our Poisson regression model. You know, remember how we had to reformulate our data so that we could use the GLM function with it. And that's the only reason why we reformulated our data. We just needed to have that frequency count on the left side of the tilde in the formula argument for the GLM function. That's it. And then we said that the first free throw attempt, second free throw attempt were explanatory variables. In the end, they actually aren't. It's just a way that we actually formulated the way that we write everything out to get GLM to work for us. That's it. And you can actually think of, in that Larry Bird example, both second free throw attempt and first free throw attempt as separate response variables. A Poisson regression model is not going to differentiate essentially between the two. That is the one advantage. Where with a multinomial regression model, you do have to specifically state you have one of your variables as the response variable. Think about how we used in the end, like the multinom function. And so that's the difference between the two. It's a very small advantage that Poisson regression models have. And I just wanted to make sure that you understand that that does exist. In the end, though, you will get the exact same results in your analysis. So now that we've been working with a Poisson regression model in a contingency table structure, you might be thinking, well, wait, could we use odds ratios to interpret then the model? And the answer is yes. So you wouldn't have to use the PC value that we talked about before. And in fact, most people would actually use odds ratios in this particular case. So for example, how would you get estimated odds ratios then with respect to our Poisson regression model? Well, what you could do is get the estimated mu values by using the predict function, and then just take your form your odds ratios from those estimated counts. That's it. Now, one could also look at what happens when you have ordinal categorical variables in your Poisson regression model. I mean, if you remember, we've looked at scenarios in chapter 3 where we have like an ordinal response. So I mean, you can have, let's say, a column variable that is ordinal in nature. How would you incorporate that into this Poisson regression model? Well, my book does discuss those topics. There's only so much that we can do in a one semester course, so that's why I typically choose not to discuss that particular topic in a course, but you're welcome to take a look at the book if you'd like to see more information on it. One reason why I choose not to discuss is that we've essentially discussed it in one way already with the proportional odds regression models. Okay, so this concludes in this section about how we can use Poisson regression models with contingency tables.